Hey, so I found this really interesting GRE problem the other day, and I wanted to share it with you and just go over it. It's definitely one of the more interesting GRE problems I've ever seen, and so I thought maybe you'd like to see it. So let's see here. Here's the problem. Oops. Okay. Let n be 60 factorial plus 55 factorial plus 50 factorial. The unit digit of n and the number of digits to the left of the unit digits are consecutive zeros before we come to the first non-zero digit. How many such consecutive zeros are there until the first non-zero digit? Wow. So this problem, first of all, is just kind of tough to read. In the first part, you first have to figure out what they're talking about when they say, that, oops, the unit digit of n and a number of digits to the left of the unit digits are consecutive zeros before we come to the first non-zero digit. Okay, so first of all, what they're doing with the question in general, it's like if you have this number, let's say 1,000, no, it's going to be 1,000, yeah. 123,000. They're saying to report these numbers, these zeros at the end of the number, okay? And so n is this huge number, 60 factorial. To remind you of what factorials are, it's just 60 factorial is 60 multiplied by 59, multiplied by 58, multiplied by just the next number down, all the way until you get to, multiplied by 2, multiplied by 1, okay? So that's factorial. It's a huge, huge, huge number, 60 factorial. And so is 55 factorial and 50 factorial. They're all gigantic numbers. So just to start off the problem, it's kind of tough. You gotta be like, okay, what are they talking about? They're talking about these zeros at the end of the number. And then they're talking about this number n, which is the sum of these absolutely gigantic numbers. And they want us to count up the zeros at the end of this absolutely huge number. At first, this one kind of stumped me. It took me a while thinking about it before it kind of worked for me. But here's how to unlock it, okay? Notice that if we're going to add up some numbers, like I'll take my 123,000 example, and then I'll add like 27, what's that, 2.7 million. And then I'll add whatever this is. We're going to add up these really big numbers, okay? Notice that these other two numbers don't matter in the context of this problem, because this problem just asks us to count up the zeros at the end, and the number of zeros at the end in a sum of numbers is just going to be equal to whatever number of zeros is at the end of the number that has the smallest number of zeros at the end. Does that make sense? So whatever number has the smallest number of zeros at the end, if we're adding them all up, that's the one that's going to determine, where the zeros are. So long as these places are all zeros for the bigger numbers. Okay. So that's an important thing to recognize for this problem, and here's why. Because remember that that number n that we're supposed to be thinking about was equal to 60 factorial plus 55 factorial plus 50 factorial. Well, first of all of these numbers are going to have, these are big numbers that are going to have a bunch of zeros at the end. How do I know? Because a 0 at the end means that there's a factor of 10. And each of these numbers has many, many factors of 10 in it. So, so that's how I know. Furthermore, 60 factorial has a lot more factors of 10 than 55 factorial, which has a lot more factors of 10 than 50 factorial. And so 50 factorial is the only one that matters. It's like this number in my little example. It's the number that is going to have the smallest number of factors of 10 out of all three of these numbers. So it's the only one we have to think about. We actually don't have to think about any of the others. So that's a big thing to unlock this problem. So now we just have to count up the number of zeros at the end of the number 50 factorial. Okay, how do we do that? Well, the number of zeros at the end of the number, any number, is the same as the number of factors of 10. And the number of factors of 10 is the same as the number of factors of 5. And the number of pairs of factors of 5 and pairs of factors of 2 we have, 5 and 2. 5 times 2 makes 10. So if we count up the number of factors of 5 that are paired up with factors of 2, okay, then we've got the number of factors of 10. Wow, okay, it seems like a lot. So here we go. But counting up the number of factors of 5 in 50 factorial is not too bad. Basically, we just need to count up the number of factors of 5 between 1 and 50. And we can just, one way to do it is just count by 5s. So you could say, well, there's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, okay? And then count up the number of factors of 5 in each of these things. Now, by the way, remember I said we need pairs of factors of both 5 and 2. Well, 50 factorial has tons of factors of 2, like 25 factors of 2. So we're gonna have an excess of factors of 2. So really all we need to do is count up the number of factors of 5, because for every factor of 5, we're gonna have definitely a factor of 2 to pair for it, and then some extra factors of 2. So really what we're looking for is the number of factors of 5. Okay, let's count them up. 5, there's 1, okay? 10, that has a factor of 5. 15 has a factor of 5. 20 has a factor of 5. 25 has 2 factors of 5. 30, by the way, the first time I did this problem, I got it wrong because I didn't count up the 2 factors of 5 and 25. But 30 has 1 factor of 5, 35 has 1, 40 has 1, 45 has 1, and 50 is 2 times 5 times 5. It has 2 factors of 5, okay? So if we count these up, it's like 8, 10, 12. There are 12 factors of 5, and there are like 20 factors of 2, so there's definitely 12 factors of 10, because every factor of 5 matches up with a factor of 2, and so we have 12 factors of 10 in the number 50 factorial, which means we have 12 zeros in the number 50 factorial, and since 55 factorial and 60 factorial all have more than 12 zeros for sure, that's the answer. That's the number of zeros at the end of this huge number, n. Whoa, that was a good problem. Honestly, this one took me some time. So anyway, hopefully that was interesting for you and made some sense. Some really good GRE problem, and I think pretty much as hard as GRE problems get. So anyway, hope you enjoyed it. I'll talk to you soon. See ya.